As we said last time, when we're taking the cross product of a vector, we're going to get back a vector. And we said that the direction of that vector is going to be orthogonal to both of the vectors we took the cross product of. So it's going to be orthogonal both to the vector A and to the vector B. But if we think about it, there's going to be two different vectors that are orthogonal to both of those. So what we want to see on the next slide is how we decide which of those two vectors it's going to be. We also talked previously about how we have the magnitude of that cross product is just going to be the magnitude of A times the magnitude of B times the sine of the angle in between. So that's very similar to that formula we had for a dot product. But again, because the cross product is a vector and not a scalar, we do have to take its magnitude in order to use that formula. So let's go ahead on the next slide and actually look at some vectors and their cross products and see how we can determine which vector is going to be the cross product that we get out. Okay, so what I'm going to do here is I'm going to put a couple vectors into GeoGebra. So it's kind of strange how we do this. I'm going to start with the vector 1, 2, 3. And we are going to enter that in parentheses, but if we just do it at 1, 2, 3 like a point, it is going to come out as a point. GeoGebra specifically, if you put a lowercase letter in front of it and say that that lowercase letter equals 1, 2, 3, then it's going to give you a vector. So that's just a little GeoGebra hack. If you use an uppercase letter, you get a point. If you use a lowercase letter, you're going to get that vector. So let's go ahead and put our two vectors in here. I'm just going to choose 1, 2, 3, and then we'll try to find one that has a good shape with that. Let's try 2, 3, -1. Okay, oops, that was just 1. Yeah, let's go with 2, 3, 1. That looks like a good vector. Okay, so I've got these two vectors here, and I'm just going to go ahead and color code them real quick so that we can distinguish them. And what I want you to think about as I'm doing this is what direction is going to be perpendicular to both of these vectors at the same time. So let's just go ahead in here and change the color of the first one to green and of the second one to blue so that we can refer to them later by their colors. So I have this green vector and this blue vector in three-dimensional space here. And I'm trying to find a direction that's orthogonal to both of those. So let's look at this in sort of the video. So I've got this green vector sticking up. I've got the blue vector sort of sticking out. And I want to try to find a direction which is orthogonal to both. So if I look, the direction over here, kind of sticking straight out this way, is going to be orthogonal to both those vectors. So I'm a 90-degree angle with the green vector, and I'm a 90-degree angle with that blue vector, if I get right in that right spot there. But if I just go in the exact opposite direction on this side, I can also be orthogonal to both there, and I'm going in the other direction, right? So it's like either going to be going this way or going to be going this way. And that's what we use the right-hand rule to determine. So how this works, I'm going to get my two vectors set up sort of the way they are, and point them towards you instead of towards me. So this is how it looks like in that picture. A is my green vector. So when I'm going to do A cross B, I'm going to start with my fingers of my right hand pointing in the direction of that A vector. And I want to put my hand in such a way that I can curl my fingers towards that B vector. So I start out pointing towards A and I curl towards B. And that tells me that the direction of my thumb, using my right hand, is going to be the direction of that cross product. So A to B, I'm going to curl that way. And so that means that my cross product should be pointing in this direction. So let's actually try that. So I'm going to type it into GeoGebra here. So we'll use cross, and then I'll just put A comma B. And that'll both give me the cross product of those two vectors, as well as give me the vector in the screen. So we can see its direction is that direction we saw. So let's do that one more time. We've got our green vector, I'll make it look like the screen, pointing out towards you. The blue vector going down. I'm going to take my right hand, I'm going to point my fingers towards A, because that's the starting vector. We did A cross B. I'm going to curl towards B, and then my right hand thumb is going to point in the direction of what we're seeing. Okay, so now let's think about what would happen if we did B cross A instead. So remember, B is the blue vector here, and A is that green one. So if I'm going to do B to A, I want to start my right hand going along B, and then curl my fingers towards A. So I notice if I put my hand down this way, I can't curl. So I have to put it in the direction of B in the way that I can curl towards A. And then again, my thumb now is going to point in the other direction, and that's going to be the right-hand rule for this one, right? So B to A, we can see is the negative of A to B, which we had talked about on the previous slide. Okay, so let's go ahead and practice with the right-hand rule. We're going to think about what the cross products are of each of these unit coordinate vectors. So when you cross product two of these unit coordinate vectors, you're going to get the third either as positive or negative. So we're going to use the right-hand rule to help us determine if we should get positive or negative in each of these cases. So let's start with I and J. So I is my pink or red vector here, J is the blue one, and K is the green one. So I'm going to use my right-hand rule here, or my right hand. And for I cross J, I need to start with pointing my right hand in the direction of that I vector in such a way that I can curl my fingers towards the J vector. So if I do that, if I point towards I and curl towards J, I see my thumb is pointing straight up. So that means that I am going to get that positive K vector. So that first one is positive K. If I go the other way, I want to be able to curl from J to I. So if I want to point in the direction of the J vector and curl towards I, then my thumb is down. So that second one is going to be negative K, because to go from J to I have got to go down. Now if we do I to K, I'm going to point in the direction of that I vector and curl up towards K. I see that my thumb is pointing away from J, so that's going to be the negative J vector. And then from J to K, again, I'm going to point in the direction of J, curl towards K, and that is going in that I direction. So there is a little shortcut if we want to remember this. It's not going to be that important for us. We're not going to be doing a lot of I, J, K crossing. But if you draw this little sort of circular diagram of I, J, and K, and we want to go in a clockwise direction. If you do I cross J, you get K. K cross I, you're going to get J. And J cross K, you get I. So if you go around in that direction, as long as we're going clockwise, we're going to get the positive version. If you go the other way, so we saw that we had gone from I to K, we're going in that counterclockwise direction. Then we get the negatives. So that's why we got I to K, gave us negative J. And if we did J to I, that gave us negative K. So you can always use that if you really want to help you determine if these should be positive or negative. But it is better practice to use the right-hand rule because that's going to work for more general vectors. So let's work through a little longer example here. The first thing I want to do is I want to find A cross B, where A is the vector 1, 2, 3, and B is the vector 0, 1, 2. So we know to find A cross B, I'm going to take this determinant of this matrix that has ijk's along the top row. A is my first vector in the cross product, so I put that one in the next row, and then 0, 1, 2. So I can take that determinant. I get I vector times 2, 3, 1, 2. The entries I get left when I get rid of the row and column for I, minus, I always remember the J comes with that extra minus sign, what we get when we get rid of J's rows and columns, plus K times 1, 2, 0, 1, which is what we get when we get rid of K's row and column. So now I can take these 2 by 2 determinants. So I'm going to get I times 4 minus 3. Remember, I multiply along the main diagonal minus multiplying along the other diagonal, minus J times 2 minus 0, plus K times, oops, I drew an equal sign, 1 minus 0. So that's the vector I minus 2J plus K, or if we want to write it in angle bracket notation, we get the vector 1, negative 2. So that is the cross product between those two vectors. Now we had seen that this vector should be orthogonal to both A and B. So to check if A is orthogonal to A cross B, what I need to do is take the dot product of those two vectors and check that it's 0. So I'm going to take the dot product of A with my cross product that we just got. We get 1 minus 4 plus 3, which is 0. So we did get that that was orthogonal. We can also double check that B is orthogonal to A cross B. To do that, we take B and we dot product it with negative 1, 2, 1. So I'm going to get negative 2 plus 2, which is also 0. So it is always true that the cross product is orthogonal to both of the vectors that we are cross producting. We just showed it in this specific example, and that's always a good way to check your algebra to make sure you didn't make any mistakes up here when you did that cross product. Okay, now we want to use A dot B to find the sine of theta. So that's kind of a weird question. It's not one that we would standardly be asked, but it's just sort of an interesting thing that we can do here. So I know that A dot B is just going to be 1, 2, 3, dotted with 0, 1, 2. So that's going to be 0 plus 2 plus 6, which is 8. And I also know that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle in between. So let's plug that in. So I get that 8 is equal to, the magnitude of A is 1 plus 4 plus 9. Magnitude of B is 1 plus 4 square rooted. And then I get the cosine of theta. So if I solve for the cosine of theta, I get 8 divided by square root of 14 times square root of 5. Okay, so we found the cosine of theta, but it asked us to find the sine of theta. What we have to use here is the fact that the sine squared of theta plus cosine squared theta is equal to 1, which means that the sine of theta is just the square root of 1 minus cosine squared theta. So let's try that. I get that sine of theta is the square root. I'm going to use the positive square root here because we're going to assume we have an angle in that first quadrant. So it's somewhere between 0, or really on the top half, so the first or second quadrant. So it's somewhere between 0 and 180. So I'm going to get the square root of 1 minus, and then I'm just going to square this cosine. So 64 over 14 times 5. So 14 times 5, let's do that out real quick, is 70. So this guy I can write as 70 over 70. So that's the square root of 6 over 70. So that's the same as, well, let's write it as that, square root of 6 over 70. Okay, so we were able to find out what the sine was just by using the dot product. But the more natural way to find the sine of that angle, especially once we've already taken the cross product, is to use that extra formula. So we just want to see that those formulas give us the same thing. So we'll zoom out a little bit more and finish this up. So part D, we want to show that the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle in between, using that sine we already found. So let's check. We know that A cross B is equal to 1, negative 2, 1. So then the magnitude of that is the same as the magnitude of this. Again, remember we can always use either single lines or double lines. It doesn't matter. I'm just kind of using both so we get used to those. So the magnitude is the square root of 1 plus 4 plus 1. So that's the square root of 6. And now the magnitude of A times the magnitude of B times the sine of the angle in between is, remember we already found those magnitudes up here. So that's root 14 times root 5 times the sine was root 6 over 70. But 14 times 5 is 70, so that becomes square root of 70. It cancels with the square root of 70 on the bottom, and I do get square root of 6. So we have verified this equality. We have showed these two are the same. So everything is consistent with itself. All right, let's get a little bit more information from this cross product. So we have this nice geometric interpretation here that the magnitude of that cross product is the magnitude of the first vector times the magnitude of the second times the sine of the angle in between. So we want to know, when is this cross product 0? So we can say again, right, as long as we assume that neither of those vectors is the 0 vector, then we know that the first magnitude isn't 0, and we know that the second magnitude isn't 0, which means that we need the sine of the angle in between to be 0. Right, so that means that the angle either has to be 0 or pi, right, 180 degrees. So if I have two vectors and they have angles 0 in between them, which means they're in the exact same direction, or, right, that's angle of 0 or 0 degrees, or if they're in exact opposite directions, so that the angle is pi, or 180 degrees, then their cross product is 0. In either of these cases, we say that these vectors are parallel. So either they're in the exact same direction or exact opposite directions. Either way, they're parallel, and when they're parallel, the cross product is 0. So then we know the cross product of two vectors is the 0 vector, because when we get a vector out, then that means those vectors are parallel. So either they're in the same direction or the exact opposite directions. Now, we could use this to check if vectors are parallel. Right, so if I want to check if vectors are parallel, we could check if their cross product is the 0 vector. Oops. But that's actually the hard way to do it. We've seen previously that the easy way to check if vectors are parallel is just to check if they are scalar multiples. So if there's one number, you can multiply one vector by to get the other one. So we could use the cross product, but it's much easier to check if they're parallel by checking if they're scalar multiples. Right? For example, if you have the vector 1, 2 and 2, 4, you can just multiply by 2 to get to the second one. So those are scalar multiples, so they're parallel. So I don't even need to worry about doing cross product, which I can't in this case anyways, because they're only in 2 dimensions and not 3. But even if they were in 3 dimensions, it's still easier to check if they're scalar multiples than to check if they have a cross product of 0. All right, we have one more application of the cross product, and then we'll do a quick recap. So I have two vectors here, the vector v and w. And we've seen when we're adding these vectors, right, we often want to think about the parallelogram that these two vectors form. In fact, this parallelogram is uniquely determined by these two vectors. So I can really use these two vectors to describe this parallelogram. And in fact, it even gives me more of that. It actually gives me the area of that parallelogram if we use the cross product in a special way. So let's think about why that's true. So how would I actually find the area of a parallelogram? I know that area, in general, is going to be my base times my height. So if I can find the base and the height of this parallelogram, then I can find the area. So the base, that's just going to be the length of that w vector. So we have to find the height. But I noticed to find that height, I always need this perpendicular here. So I formed a right triangle whose hypotenuse is v. And then I have this angle theta, the angle between my two vectors. So this guy, we should have, it's an opposite, so we should get sine of theta is equal to that height over the magnitude of v. So the height itself should just be the magnitude of v times the sine of that theta. But now we should recognize this, right? Magnitude of w, magnitude of v times the sine of the angle in between. That's exactly equal to the magnitude of the cross product of those two vectors. So to find the area of the parallelogram spanned by two vectors, all you need to do is take the magnitude of the cross product of those two vectors. Sometimes they'll instead ask you for the area of a triangle spanned by those two, but as long as the triangle is only half of the parallelogram, you can find the area of the parallelogram and then divide it by 2, and that gives you the area of the triangle. So that's another little thing you might see sometimes. Okay, let's go ahead and finish up by just doing a little recap, compare and contrast of our dot product and our cross product. So the dot product you can compute for any two vectors, right? So they can be in Rn. As long as they're the same dimension as each other, it doesn't matter how big they are. Where the cross product you can only do if you're in R3. So that's a big difference between the two. The dot product gives you a scalar. It just gives you a single number back, where the cross product gives you a vector. We can use the dot product to check if two vectors are orthogonal. In order to check if two vectors are orthogonal, we check that their dot product is 0. And we use the cross product to get a vector which is perpendicular to two other ones. So we check using the dot product, but we get a vector perpendicular to two other ones using the cross product. The dot product itself is a scalar, so it's equal to the magnitude of A times the magnitude of B times the cosine of the angle in between. And for a cross product, we have a similar formula, but it's the magnitude of that cross product equaling the magnitude of A times the magnitude of B times the sine of the angle in between. We can use the cross product to check if vectors are orthogonal, but it's easier to just check if one is a scalar multiple of each other. So those are sort of the big things we need to know about the dot product and the cross product. You know, we also should know how to compute both of those, but these are sort of the big things. Especially for cross product, the main thing that we're going to use it for is to find a vector orthogonal to two other vectors. So that's a really important thing to remember about that cross product.